In this lecture, we will talk about the algorithm to find the maximum matching in a graph efficiently. And before discussing the actual algorithm, I want to describe an applications, which is very interesting actually. So this is an application in the medical system, the hospitals. So in 2005, there was a news in Korea where two families exchanged their kidneys. So this, let's say you have two families. One person has a sick kid, and one person is sick because they have some issues with kidney, but the husband couldn't donate his kidney to his wife because their blood type didn't match or whatever. For some reason, his kidney cannot be used. And same thing with the other family. So his kidney cannot be used for this person. So what they did is to find the two families and convince this person to donate the kidney to sick person over here, and convince this person to donate the sick person over here. Right? This way, everybody is happy. So this is what's called the kidney swap or kidney exchange. So if you have many families having sick persons, right? So having some problem with the kidneys. All right, can I draw like this? All right, and you can put an edge if they can do this exchange. I might have a graph like this, right? So this becomes a graph problem. So which pair of couples would you do the surgery? Maybe I do here. I mean, if I do here and okay, that's, I mean, it's not part, like, for instance, if I make a exchange over this couple, then no further couples can get any surgery. Whereas if we do surgery over this pair, then you can save 4 patients, right? 4 people will get new kidney, so they will have a much better life. So the objective of this thing is to maximize number of pairs you choose. And this is exactly the graph theory problem that we are going to discuss. And this was not observed until 2004, right? So there was an interesting article published in Time magazine in 2005 about the story how this scheme was discovered. And if you Google their names or this kidney exchange and graph matching, you can read the interesting articles. And basically, this husband, at that time they were not married. This surgeon was dating with some lady who was mathematician, and the surgeon was telling her that in his hospital, one of the problem is to find the maximum matching, and they were doing ad-hoc method because they didn't know how to do it efficiently, and she realized that this is a graph theory problem, and she reminded herself that there was an advanced algorithm which we are going to learn, right? So it's good to learn this thing, right? So in this magazine, it says that based on the algorithm created by the Canadian mathematician Jack Edmonds in 1965, in 2004 they were able to use that to efficiently pair the couples to maximize the number of surgeries, number of kidney exchanges, which will save more people. So now you can say that graph theory saves lives. Okay, so let's go back to the lecture. All right, so how do we have an algorithm? And actually, if we go back to our proof for Koenig's theorem, right? Remember the proof of Koenig's theorem? We use the fact that graph has, matching M is maximum if and only if you don't have augmenting paths. All right, so for the algorithm, maybe I start with the vertex which is not covered by any matching and try to go, and then I want to have an augmenting path, so next edge I choose a matching edge, and then I try to choose any random edge, and then continue. This is an M, this is an M, and continue, and then this is in M, and continue. And if I'm lucky, I will be able to find an augmenting path. If I find an augmenting path, then I'm happy, and then I can increase the size of M by 1 by deleting those red edges from my matching and adding these black edges to the matching. That will increase the size of matching by 1. So you may think that this is done, right? I mean, there are only finitely many possibilities to find an augmenting path, right? Graph is fixed. I mean, number of vertices is finite, and there are only finitely many possibilities to have an augmenting path. If you search them all, if no augmenting path exists, then this says that your matching M is maximum, and otherwise you can increase your matching by 1 and then continue. And is this best possible? And this is what people thought in 1950s or 60s, and maybe early 60s, because at that time there was no concept of the polynomial time algorithms. People never thought about polynomial time algorithm as a way of telling an efficient algorithm. And for this problem with 10 vertices or 12 vertices or 1,000 vertices, you still have a finitely many cases, and people thought that okay, it's done. But then Jack Edmonds, who's a Canadian mathematician and is known for this his breakthroughs in matching theory and combinatorial optimizations, he came up with this new algorithm where polynomial time new algorithm has a polynomial running time, and while doing so, he had to convince others that his algorithm is better than this naive algorithm by looking at all possible augmenting paths. So what he came up with this concept of polynomial time algorithm, right? He wanted to argue that this is the distinction between previous algorithm where you search all possible augmenting paths, whereas in this algorithm you don't need to worry, you don't need to spend like exponential time or more than that, right? So you only need the polynomial number of steps. Okay, so this is well, I mean, but still this is the basis of the algorithm, right? We want to find the augmenting paths, but the problem is how. And what we could do is build a directed graph, right? So how do we build a directed graph out of graph with M. So you have graph G and matching M. Now I put an edge, right? So if I have an edge like this together with that, then I put the shortcut, right? So this is X, Y, G, then I put shortcut X, Y, G. Why is this useful? Well, what I want is I want to find the augmenting paths, and augmenting paths look like this. Okay, let me 1, 2, 3. This is what it looked like. And now in this auxiliary directed graph, what you have is this directed path from a vertex not covered by M to a vertex which is a neighbor of vertices not covered by M. So this is what you do. You start with this first build this directed auxiliary directed graph, and then try to find the path from vertices not covered by M to its neighbors. Okay, let's say this is X, this neighbors of X. Now we want to find the directed path like this. Okay, now but not all directed paths gives you an augmenting path. If we are really lucky, then we may get the augmenting path, right? And this is a neighbor of somebody, so it's a neighbor of somebody. If we are really lucky, you get an augmenting path like this. But if you're unlucky, maybe there could be issues. Maybe these two vertices could be equal. Is it possible? Could they be equal? No, because if they were equal, when you arrive at this vertex, you have to use a matching edge. But there's only one red edge instantly with this vertex. So if they were equal, then you cannot have two red edges coming here. So these black vertices which were hidden are all distinct, right? How about the vertices here? Well, these vertices are also distinct because it's a directed path. It's a path in a directed graph. So vertices are distinct. So they are distinct. These are distinct. So it looks okay. No, maybe these two could be equal. Well, that's the problem. So the problematic case, here's the problem. It is possible that X is equal to Y. So what does that mean? Well, how does it look like? It looks like this thing together with the red edge, and then you go, so this is X, you go with this, and red, you go with that, and then here's Y, and you end, no, it's not Y yet, and then you end up with, okay, so this, you end up with this, oops, black edge. If they are equal, and then it continues, right? And this doesn't give you augmenting paths. So that's the problem. And this problem doesn't occur if graph is bipartite. So this method, so this naive method of using the auxiliary directed graph gives an efficient algorithm to find the M-augmenting path in a bipartite graph. Because in the bipartite graph you don't have any other cycles, so you can never have these two vertices to be equal. So all these vertices are distinct, all these vertices are distinct, so therefore there's nothing to worry. Yes. So the only problematic case is when graph has another cycle and it happened to be this cycle. So the algorithm, oh, by the way, there is an algorithm in a directed graph which says whether or not you have a path from A to B. And not only that, you'll find the path. I'm not gonna cover it, but this is a well-known algorithm. So in general, it may look like this. So you have red, black, and red, and then black, red, black, red, black, red, black, red, black. This could be the graph that you may have obtained from directed paths, right? Yes. Okay. So what happens? What do we do now? Well, first of all, what I would like to do is to remove those two edges from M and add these two. So this is what we call the augmenting. So I'm gonna change M to M prime so that M prime looks like that. Okay, so that way I make sure that this vertex is not covered by M prime, right? And that's what we are doing now. So anyway, this initial setting is called the M flower. Later we will say, right? So okay, well, what should I say? If I call this an M flower, then there is an efficient algorithm. Okay, but for computer science people, I would say polynomial time algorithm. To find an M augmenting path or on M flower in G, right? This naive method of using auxiliary directed graph will either, right, this method of using auxiliary directed graph and use shortest path algorithm will either give you the augmenting path, in which case if we are very happy we can augment the M to increase size of M and then run this algorithm again, or we are stuck with the flower. And the flower never happens in a bipartite graph, so in a bipartite graph this already gives you an algorithm to find a maximum matching. But in a non-bipartite case, you may end up with this flower. And whenever you have a flower, okay, I should have drawn the flower like this, right? Whenever you have a flower, you can cut the stem and then make a cycle by replacing m by m prime. Oops. So that's the setting of the next lemma. This is called the cycle shrinking lemma. Okay. And here's the situation. So let M be a matching of G and C be a cycle of length 2k plus 1 with exactly k edges in M and one vertex of C is not covered by M. Now in this case, what we're gonna do, right, we have a cycle, every other edge is in the matching, and there is one vertex, so this is other cycle, one vertex which is not covered by matching. So whenever we have a flower, we can augment to make a cycle like this. And what we're going to do is to contract this into one vertex. So let G prime be G contract edges of the cycle. So they become single vertex. Let M prime be the M minus edges of the cycle. Now what we claim is M prime what will be the best way? Okay. Then M prime, okay, M is a maximum matching of G if and only if M prime is a maximum matching of G. G prime. So in other words, if we after shrinking, we apply same algorithm to find the augmenting path. If it doesn't find an augmenting path, then by this lemma we knew that the bigger, M is a maximum matching. There will not be any augmenting path. Also, maybe I should say that if G prime has an M prime augmenting path, then so does G, and okay, G has an M augmenting path. Is that a better formulation? Maybe. Let me say it this way. Okay, so, and not only that, in the proof you will see that if you have an augmenting path, you can convert it to augmenting path of the other graph. Okay, so that gives you the algorithm. And these two things are actually the same thing, right? The graph has augmenting path if and only if you don't have a maximum matching. So there's equivalent thing, but I wrote it twice. And I will try to prove in the second form. So suppose G prime has an M prime augmenting path P, So let's call this vertex to be this is vertex V, and this vertex is right. If you have an augmenting, okay, let's say this is V again. If let's use black. If P uses V, then what does that mean? Since V is not covered by M prime, P is a path ending at V. So then, if you have a path like this in G prime, then in G, it arrives at some vertex, and now some vertex of the cycle in G. And now the thing is, the last edge is not in the matching, right? And now it's possible that this vertex is matched by an edge in the matching, but C has one vertex which is not covered by matching. So how do we complete this into an augmenting path? Well, depending on the location of the red edges, you follow this path, right? So you end following this path, and then at this vertex you follow red edges, going around the cycle you arrive at V, right? So in G, so we can extend P along C to make an M augmenting path of G. So this gives a proof of one direction. So if G prime has an M augmenting path, yes, if G prime has M augmenting path, then so does G. Okay. Now what about the other direction? So if G has an M augmenting path P, right? So this is P, and now we want to show that G prime has M prime augmenting path. Then it is an M prime augmenting path of G prime if P does not use V, or P does not visit V, C, right? If C was outside, then this again stays as it stays as an augmenting path, so nothing to show. So we may assume P visits some vertex of C, W of C. And we may assume by reversing P that P starts at a vertex not in C, right? Because the first vertex of P are not covered by M, last vertex of P is not covered by M, but C has only one vertex that are not covered by M, so therefore one of the end will not be covered. So let's say the first vertex is not covered by, not in C, so this is not in C, and this is first vertex. So let's look at the subpath let P prime be the subpath from the starting vertex to the first vertex to W. Yeah. With the minimum length. So it's the first vertex that you arrive at C. Now, if you arrive at the vertex V, if W is equal to V, then this is augmenting path of this is an M prime augmenting path of G prime, right? So we may assume that V is not equal to W, so that means the last edge is black and you go around, right? There are edges going around. But again in this case, P prime is this part, right? And it's still an M prime augmenting path. Okay, so that's the proof, right? When you contract, you end up with a cycle, and this is V. Okay, so that's the cycle shrinking lemma. And how do we use that to have an algorithm? So here's the algorithm. If you are familiar with the recursive programs in computer code, then you may feel slightly easier. So you start with the empty set as a matching, and build the auxiliary digraph, directed graph, find find an M augmenting path or an M flower, right? And then if we find an M augmenting path, then we replace M prime by M delta EP and start again. Nice, we go here. So we can assume that there's an M flower. So if we have an M flower, then by taking M prime, we may assume that the stem, if you have a flower, that's a stem, right? Has length 0. Once we do that, then contract C and run this algorithm. To find the M augmenting path, M prime augmenting path. Okay, maybe I should say it's not an algorithm. Instead of saying it's algorithm for finding maximum matching, I would say it's algorithm to find an M augmenting path. So then instead of saying start again, we just say done, right? Now, we run this algorithm recursively, but now when you contract it, the graph gets smaller, so the recursive function never run into the infinite loop. It will eventually stop. So we find an M prime augmenting path, that's the output, and convert it to a M augmenting path. Yeah, I should say if exists. I also should say if exists. Right. So what is the output? Well, output is either this, or it says, oh, there's no M augmenting path, or it runs the it calls this subroutine again with a different graph, with a different matching, right? M prime, and then G contracts C. But you keep reducing, so initially you start with the graph G and matching M. Whenever you find the flower, you have a new graph and new matching, new graph, new matching. So the algorithm will keep contracting. But these contractions cannot repeat indefinitely because each contraction will reduce number of vertices by at least 1. And number of vertices in the initial graph is finite, so eventually it has to stop. And when it stops, it means it will give me an augmenting path, or says, oh, there's no augmenting path. And then you go back and back and back and back, and then they will be converted back. So here, if this says that there's augmenting path, then this will find augmenting path, and so therefore you can find augmenting path. Right? If this says that there's no augmenting path, then by our lemma, this doesn't have augmenting path. Okay, and all of these things can be done in polynomial time, right? So the number of steps you go in is at least linear, right? And then inside you run this algorithm to find the, I should say ON, the depth of recursion is little big of n. And then each step it takes polynomial time, so it's n times some polynomial, so still it's a polynomial. So that's how the algorithm of Jack Edmonds, who used to be a professor at University of Waterloo, is still alive. He's still living in Waterloo, and this is 1965, which was mentioned in Times article. Okay, so that's the Edmonds algorithm. All right, as a final topic, I want to discuss stable matchings. Now we change our thing slightly. This is the last topic on matchings. So imagine that you have boys and girls. It could be students and schools, right? Each student want to go to school, but now, okay, not many students, schools, but okay, professors. So the graduate students. So they need to pick an advisor, but let's say professors want to take only and most one students, and students have choices. Professors have choices, but sometimes they will be unhappy if the choice is not optimal. What do I mean? Okay, so let's say you have two people, A and B, and two other people, C and D. And let's say A is matched to C, B is matched to D. But what if A likes D better? A thinks that D is better than C, and D thinks that A is better than B. Then they have both A and D could withdraw this pairing and then make a new connections, making these two people singles. And what end up is a matching of smaller size, but both A and D are slightly more happier than the previous scheme. So here the objective was not really a maximum matching, but something stable. We want to find the pairing that stays. The people will say at least that there's no two people who could agree to break their current contract and move on to a different pairing. So this is what's called the unstable. And so how do we define it, right? So suppose that each vertex of a graph G has an ordering of edges incident with V, right? So you have edges and you say, oh, okay, now this is smallest, worst possible, and this is slightly better, this is better, best, okay? But so this is according to A, but according to B, she may think, okay, this is best, but maybe 1, 2, 3. So every vertex gives a preference, right? So the larger number is the better, or ordering, right? So ordering of the edges. So when is M stable? A matching is stable if it's not unstable, right? So let me say what is unstable. When is it unstable? Well, if there's a pair V and W, right, which are adjacent, if there exists an edge VW in graph G minus M, right, such that now both of them are happier, right, happier than the current partner. So V prefers that, right? Right. So for any okay, what should I say? For every edge, okay, let's say this is E. For every edge F in M, sharing, okay, let's not say VW. I don't have to say VW. For every edge sharing on end v with e this person v prefers e than f. So this is what's called the unstable. Right? So you have an edge, and for any matching edges, this person prefers that black edge, and this person prefers that black edge. And this covers the case when one of them is single. So this person, there's no matching edge covering that. This person, I might have a matching edge, and she prefers that, and then that's unstable. Because these two couple have incentive to break their current matching. So what is a stable? So let me define stable more properly. Stable if for all edges E and M, yes, I'm just negating everything. There exists an edge F in M sharing an end V with E such that F is not preferred. Okay, so I should say the other way around. Right? And I'm assuming that this ordering is full order, so you don't have tie. Total order, yeah, so you don't have tie. All right, so that's the definition of stable matching. Now here's the theorem due to Gale and Shapley. In 1962, saying that every simple bipartite graph has a stable matching. Right? Okay, and due to this work, Shapley got the Nobel Prize in economics. Okay, so can you see this screen? So this was in 2012. This mathematician and economist, Shapley got the Nobel Prize with some other person, not with Gale, because Gale passed away before this Nobel Prize. So the prize motivation was for the theory of stable allocation. So this is about the stable matching and practice of market design. So what they did is to design a system of markets so that things are distributed. After distributions, nobody will complain, and nobody can complain. The things will stay stable. That's the motivations. Okay. Yeah. Proof. So how do we prove this? So instead of this ordering, I will give a number. So for given, okay, I will assign number. So first of all, let A be the bipartition of G for each vertex. Point B, this assigns an integer by e to an edge in okay, integer from 1 up to degree of this vertex, so that edges get numbers from 1 up to degree. So E is less preferred than F if and only if phi of E is less than phi of F. Okay, and let's give a distinct integers. Right, so what in the picture it's easy, right? So I give, so every person on the right hand side, on the B side, give a ranking of the edges based on her preference, right? So 1 is the least preferred and the degree is the most preferred. Now every edge has some number. Now I didn't yet take account of the preference on A side. Right. So what we're gonna do is as follows. So it's kind of an algorithm. So every people in A propose to their best neighbor, right? So each vertex in A propose to their best neighbor, and then people on B side will either accept it by rejecting the previous one, or just decline this propose. And then they continue. And they continue until no further changes are made. And the theorem is that this will be the stable matching. So let's see how we prove that mathematically. So what we're going to claim is the following. So there exists a matching M with the following property. For every HE AB in the matching with the A is in A side and B is in B side. So whenever I have a matching edge, then, and if this man likes some other person better, some other lady better, then this woman has a reason to decline A. Well, so A prefers C than B, then okay, C will think that, oh, I don't like A because my current partner is better. So for every edge E in M, if E is less preferred than F for some edge F, which is AC, then F, so C think that, okay, F is not good. No, F is not good because I'm currently have a better partner in M. Okay, so that's the claim that I want to maintain. And how do we know that such a matching exists? Well, empty set satisfies, okay, so let me say this is 1. Empty set satisfies 1. If I have an empty set, then there's nothing to say, right? There's no, I mean, this says that for every edge in M, some property holds. So when M is empty, then this holds because there's nothing to check. All right, so you must have, so there exists a set satisfying 1. Now among all matchings, you choose M such that such that the sum of these edge values is maximum. Okay. There are only finitely many matchings to consider, and among all matchings satisfying this one property 1, I want to choose the one that sum of the values of the edges is maximized. And then the claim is M is stable. So suppose not. If M is not stable, then there exists an edge, right? I'm just copying from the left hand side. As E in the left hand side, such that for every edge, for every edge E F in M sharing an end V with E, then E prefers F, right? Okay, so we find the sum edge E in the matching. And let's say AB is equal to E, so A is in A side and B is in B side. So this is AB. Now, what if A is a single? If A is not covered by M, then according to this condition, right? Or let's say, okay, if A is not covered by M and B is not covered by M, then we don't lose anything, okay? We may try to add that M prime be M union E, okay? And then does it satisfy the property 1? I want to say that M prime satisfies property 1. Yeah, this property. Hopefully it could be good if it satisfies, but actually not quite, because it is possible that this was the edge that I'm adding. Okay, what's going on? Oh, edges. This edge, yeah, this edge is not in M, right? So I was confused. Yeah, this edge is not in M, right? So if this is the case, well, what happens if I have a better edge? Right, so A might prefer some other person on B side than B. And if this person is single, for instance, then we have an issue, because that it doesn't satisfy property 1. But how do we ensure that something like this doesn't happen? So what we do is choose E specifically. So choose, so among all edges incident with A satisfying such property, choose the most preferred edge by A. Okay, so when I choose E, I'm not choosing arbitrary one. I'm choosing the one so that if I go a little bit slightly better one for A, then there was a reason why this one doesn't satisfy this instability condition. So this is not in M, but because so that case is just stable, right? So that means either this person, so let's say B prime, likes the current partner better. Yeah, I mean that's the situation, right? That is the situation. Right? There exists no edge E such for every edge sharing an end. With E, you have this preferred condition, so I'm gonna choose A, so that among all edges instead with A, we choose the one with maximum, most preferred one. So if I have a bigger, if I have a B prime, which is preferred, and if they are adjacent, then because of this condition, this should fail. This condition should fail for B prime, AB prime. So that means there exists F here, right? So this vertex B prime is currently married to someone else, so which she thinks that this person is better than A. So that's why under this assumption, M prime satisfies 1, because if I put this into M prime, now when I look at any edge more preferred by A, then by these conditions, this vertex will have another edge in the matching which she prefers. And that's precisely the condition 1. Right? So this is a key step. Okay, so if A is not covered by M and B is covered by M, what does that mean? If A is not covered, so A, E, but B is covered, and because of our assumption for every edge sharing end, and this is the assumption, so therefore B would prefer this edge. So then we replace M prime by M minus E union, M union E minus F for the edge F in M instead with B. Now the thing is, phi of M prime, which is the sum of the edges in M prime, is strictly bigger than phi of M. And does it satisfy 1? I hope so, because we are adding this edge into E, and again by the same logic, right? if you have a better one, then there was a reason why we didn't choose this edge, because say B prime actually prefers someone else. So it's by same logic here, it still satisfies 1, and the value is bigger, that's contradiction. Here again, here's the same thing, so the value is bigger, so it's contradiction. Okay, now finally, if A is covered by M, what does that mean? So A was covered, so there was a matching edge, and by unstability condition, that means A prefers this black edge, right? But then by the property 1, B would actually prefer the other edge. An edge in M, then E, contradicting the assumption that M is unstable. So this case doesn't happen, right? So that basically gives you the proof, right? So whenever I choose a matching satisfying this property 1 and have the maximum sum of these values, it will eventually, maximum sum of the values, and it is stable. Okay, now why does this give a proof algorithm? Well, this whole step is an algorithm. You start with the empty set and you find an edge like this, and then you do operation like this. So from M you get M prime, and that will increase the sum of these values, and some of these values cannot increase forever, right? Phi of M is always less than or equal to number of edges times, it's a sum of degree, let's say, which is actually equal to number of edges, right? So the number of iterations is bounded by number of edges of the graph tree, so it can never continue forever. So at some point it has to stop, and that's when we know for sure that the algorithm found the stable matching. Okay, and this has been used in many places and has many applications, and that's why Nobel Prize was awarded. So sometimes a few years ago in the CS department, they use stable matching algorithm to assign students to professors, and in US, after the medical school, the students from medical schools are assigned to the hospitals to do resident, and this assignment is also made by using a variation of this algorithm to assign stably. And some in New York, in Boston, the middle school students are assigned to I think it's high school, probably. The students are assigned to high school based on the preference, and the school choose preference based on something, and then this assignment is based on the stable matching. So they have lots of applications. Anyway, that's it. So we finished the matching. So in the next lecture, we will talk about connectivities.